All right, let's do a couple examples with the intermediate value theorem and the squeeze theorem. Let's start with this one. Verify that the intermediate value theorem applies to the indicated interval and find the value C guaranteed by the theorem. Here's what it means by verify. For the intermediate value theorem to work, this y value that we're shooting for has to fall between the function when it's evaluated at A and at B. So we need to find f of A, we need to find f of b, and we need to verify that 11 falls between those two numbers. All right, so let's do it. If I plug in 0, I get 0 squared plus 0 minus 1 gives me negative 1. And then f of 5 squared plus 5 minus 1, what is that? We got 25 plus 5 is 30, minus 1 is 29. Okay, so that's the first part. But now to verify that the theorem applies, this number has to fall between those two values, and it does, right? Just for solving a problem, that's enough to say, yeah, we can use the intermediate value theorem. If I were, writing an answer on a test, maybe an AP test, if I wanted to say, yeah, I verified it, what I would write down is I would say, yeah, I found f of a, and it was less than that value, and that was less than f of b, so I can say that the intermediate value theorem applies. That's how I would show that I had verified the intermediate value theorem, saying yes, 11 does fall between f of a and f of b. Now we're ready for the second part. Find the value of c guaranteed by the theorem. So because the intermediate value theorem applies, I know that there is somewhere that this function equals 11. So to find that value, we just solve that equation. So I'm going to say x squared plus x minus 1 equals 11. And I'm going to solve that for x. And this part right here is going to be the hardest part of these problems, is doing the algebra to solve for x. But let's see what we can do here. I see that it's quadratic, so I really want this to be in standard form where it's equal to 0 on the right side. So I'm going to move that 11 over here. And then what I'm hoping for is that this is something I can factor. So I've got x and x. I need factors of 12 that will subtract to give me 1. That would be 4 and 3. The signs are negative, or sorry, the signs are different. The larger one is positive. And so I've got that x can be negative 4 or x can be 3. Now I don't really have two answers here. Recall, we're in this region right here. I've got to be between 0 and 5. That's my interval. So negative 4, not in my interval. So I just put my box around x equals 3. That is where that function will have a value of 11. Let's do another one. I think that's as hard as they get for intermediate value theorem. Let's go on to squeeze theorem. Okay, suppose g of x is less than or equal to f of x, which is less than or equal to h of x. This is your red flag that this is a squeeze theorem problem, because what this is telling you is it's telling you, okay, you've got g of x, that's less than f of x, that's less than h of x. So now if it's asking me about f of x, that function in the middle, I know this is going to be a squeeze theorem problem, that h of x is going to meet g of x somewhere, and then f of x has to fall in the middle, which means they all have to have the same limit at that point where they get squeezed together. So to find that value is pretty easy. All you have to do is take whatever that limit was and plug it into each function. That should be that L value at that point, which is going to tell me, yeah, that's what f of x has to be there as well. So let's do this. Let me erase all this rubbish here. That was easier than going to the next slide so I don't lose all my equations. Okay, so I'm going to plug x equals 2 into g of x and into h of x. So g of 2 is equal to, it's just negative 1. There we go, that was easy. And then h of 2, now here's the thing, it should be equal to negative 1. If h of 2 is not equal to negative 1, then the squeeze theorem does not apply at x equals 2, and I can't solve this problem. But it's a textbook problem, so I'm feeling pretty optimistic. So we've got 2 squared minus 4 times 2 plus 3. So what is that? 4 minus 8 plus 3. So negative 8 plus 7. Sure enough, that is negative 1. So if g of x is negative 1 and h of x is negative 1 and f of x falls between them, that means f of x also has to be negative 1. So find the limit as x approaches 2 of f of x is negative 1. Let's look at one more. Use a graphing calculator. Whew, got some relief. We've got some permission to use a graphing calculator. To graph the function and y equals absolute value of x and y equals negative absolute value of x in the same window. So here's my function. We want to do that and that and that all in the same window. Use the graphs to observe the squeeze theorem and find the limit as x approaches 0 of f of x. This is an interesting function, right? If I just plug 0 into this, I've got 1 over 0 inside my trig function. That's undefined. I can't do it. So I have to use some other method to figure out the limit. And here we're going to use the squeeze theorem. I don't even have to graph it. I know what this is going to be. Absolute value of x looks like that. The negative absolute value of x just takes that and flips it over. So at x equals 0, that L value is 0. So I already know the answer. The limit as f of x approaches 0 is 0. But we'll humor them. We'll go graph it and see what that function looks like, because I have no idea what that one looks like. So let me switch windows and we'll go over to Desmos. That would be a fun one to use right now. Okay, if you've never used Desmos.com before, it's a nice graphing website. It's less cumbersome than using your calculator. You certainly could use it on the AP test, but it's fun for this demonstration right here because of the nice colors and everything. So I've already graphed y equals absolute value of x and negative absolute value of x, and it did exactly what we expected it to do. Meets right here at y equals 0. So I know if this question is asking me to use the squeeze theorem, then my new function must fall between those two graphs, and the limit's going to be 0. Let's turn it on and see what it looks like. Ooh, let's see what we've got going on here. I'm going to zoom in on this. Look at that, it's oscillating between those two functions. Look how perfectly it fits in between those absolute values. Now we've seen before that when a function oscillates like this, that we can't actually find the limit. But it turns out we can, using this trick of the squeeze theorem. Look at that. How interesting is that it fits so perfectly between those absolute values? Can I ever get to a spot where it flattens out, or does it just oscillate infinitely? It's just going to keep doing this. This is fun. Like I'm walking down a corridor. Okay, I'll stop. So we've used the squeeze theorem to see a function squeeze between two other functions and used it to find the limit.